Sulfate is a big deal because it has become a divisive issue in Minnesota, setting mining against environment. I think that's a false choice. There's no reason why we have to choose between supporting mining and protecting the environment. Native tribes, environmentalists, and much of the scientific community says that excessive sulfate damages wild rice and causes an increase in mercury contamination in fish. The mining companies dispute this, saying that the sulfate standards are too rigorous, unnecessary, and far too expensive to comply with. The fact is, we do have a legal standard of 10 milligrams per liter of sulfate for wild rice producing waters. This is a division that has caused a delay in the development of many iron resource projects. It is something that we can do something about. We're going to talk now about a three-step technology and a possible solution that would help us bridge the divide between mining and the environment. As you already heard a little bit, I moved to Babbitt, Minnesota, and the shores of Birch Lake in 1959 because of taconite mining. I know how important iron mining is, and I know how important our natural environment is. After studying mechanical and environmental engineering at the University of Minnesota, I worked on filtration and water treatment in Brazil for 30 years. After returning to Minnesota, I worked on floating treatment wetlands. What are these? These are man-made islands that biologically help improve and clean up the water around and under the islands. In the course of this work, I commented to Mark Reinsel, a mining remediation engineer in Montana, about the sulfate standoff issue in Minnesota. He said the perfect place to do sulfate reduction is under a floating island. There, the microbes will consume all of the available oxygen. Once that oxygen is gone, the microbes will then begin to strip the oxygen off the sulfate, producing hydrogen sulfide. Follow nature's lead for the reduction of sulfate, Mark said. And so now let's take a look at what nature does for removing sulfate. Sulfate, that's sulfur with oxygen, in the surface water where there's plenty of oxygen available, stays as sulfate. Now, as it migrates into the mud and sediment, the microbes there consume all of the available oxygen. So then the sulfate-reducing bacteria take over and begin stripping the oxygen off of the sulfate for them to breathe as they continue to consume or eat the biomass. This is a biological process that produces hydrogen sulfide, sulfur with hydrogen. This is that terrible smelling rotten egg smell that none of us like, that's toxic to you and to me and to wild rice. It's not sulfate, it's sulfide that damages the wild rice. And so this is a process of nature. done by sulfate-reducing bacteria. But there's another concern with sulfate-reducing bacteria. As they decompose or consume the biomass in the sediment, they are thereby releasing sequestered mercury that's been built up in the sediment. And they furthermore methylate this mercury, converting elemental mercury into methyl mercury. And it's methyl mercury that is soluble in water and in fat and gets into the food chain, accumulating in fish and the humans who eat the fish. We know how dangerous mercury can be, particularly for children and pregnant women. So after considering and consulting with many different specialists in sulfate reduction, we asked, can we reduce sulfate following nature's lead biologically without causing any of these bad side effects? After this consultation, an idea was born in 2008. We designed a floating bioreactor. This is essentially a big plastic bag, heavy duty, with flexible sides, so they can withstand the movement of ice in the wintertime. This encloses about 4,000 gallons of water, floating, and we can fill it with fiber for the sulfate-reducing bacteria to attach to and stay in place. We use a fiber that is non-biodegradable, low-cost plastic fiber for them to attach to. With the recycled fiber we use, can put 25 acres of attachment surface area in just 49 square foot area. This is a really concentrated wetland effect that can grow a tremendous population of sulfate-reducing bacteria. We deploy these bioreactors by floating them and circulating water into and out of them. This takes the sulfate to the sulfate-reducing bacteria. We feed them, we monitor the results, we keep it flowing all year round, and we avoid any methylation of mercury. These bioreactors are rafted together to make big rafts or small rafts of bioreactors, sulfate-reducing bioreactors. We float them in a mine pit lake or a tailings basin where there's a high concentration of sulfate. Deep in these water bodies, there is very little dissolved oxygen. And also, there is extremely low mercury, often non-detect mercury. If there is no mercury present, we cannot methylate mercury. Furthermore, when we float these in a mine pit lake, the active working volume is below the water surface. It is below the freeze zone, where water can always flow and where the temperature is relatively constant to keep those sulfate-reducing bacteria happy and continually reducing sulfate. This is a modular system that we can start small and build it up with many different ones to handle any size flow we need. It is meant to treat the water that is needing to be discharged from a mine pit lake or a tailings basin before it goes downstream. To do this next development, next parts, we needed to prove the durability of these modular designs, and we had to figure out how to eliminate the hydrogen sulfide. For this, we got funding and collaboration from some excellent partners. The IRRB, the Iron Range Resource and Rehabilitation Board, the NRI, the Natural Resource Research Institute, Mid-Drive of the University of Minnesota, the East Range Joint Powers Board, Cleveland Cliffs, Polymet, and RNAS remediation projects, all assisted with funds and collaboration at various different parts of this development. At the end of this, there was a report by NRI in July of 2017. That report concluded that we regularly achieved over 90% sulfate reduction. And at times, or often, 100% reduction, even in wintertime. And no methylation of mercury. These rafts lasted for, because the test only was for 4 winters, lasted all the way through with often 100% sulfate reduction, even in winter, and no ice damage through that whole period. With this, we demonstrated that we could reduce, in a real live application, over 1,100 milligrams per liter of sulfate to below the wild rice standard of 10. This was a great achievement, but we needed to pursue further on things on that. We then moved to a lab scale test where we could control all the different parameters and come up with the best parameters for consistent sulfate reduction. This graph that you're seeing here starts with water from the St. James Pit Lake near Aurora. This pit lake has water with about 300 to 400 milligrams per liter of sulfate, which is the blue line, the upper line there. And so it's between 300, 400, depends on the time of year, etc. But we consistently had a reduction of over 99% of the sulfate. The resultant sulfate levels is the red line at the bottom. It's got some spikes when we change the water flow, etc. That's the final sulfate levels, very close to zero over time. But that result is converting sulfate to hydrogen sulfide. That's not a good final result. We can't stop there. We have to do something with the hydrogen sulfide. So we ask, can we follow nature's lead and use iron to remove the hydrogen sulfide? We got lots of iron around here. Taconite. It is not effective for this. Why? It is iron oxide. It is already bonded up very tightly with oxygen. Will not react very well with hydrogen sulfide. And it's not conductive. But the good news is direct reduced iron, DRI, will. DRI is the iron we need to be producing on the Iron Range. With DRI, we can make green, non-polluting steel in Minnesota. DRI is over 97% metallic iron. Why? It has had the oxygen removed from it. It is very porous and very reactive to hydrogen sulfide. And it's electrically conductive, or taconite pellets are not. We can make electrodes out of DRI. With these electrodes, we apply a low DC current between them, causing positively charged iron ions to move from one electrode to the other. As they go, they encounter negatively charged hydrogen sulfide ions. They immediately react, forming iron sulfide. If you look closely at the video there, you can see the black iron sulfide forming as that iron encounters the hydrogen sulfide. And it's cascading down. We can separate the iron sulfide through precipitation and form a slurry that we can pump off and remove the sulfur from the system. This is a graph of actual results, that same 9-month time period from the sulfate, where the upper red line is the sulfide produced from the reduction of sulfate, and the bottom blue line is the remaining sulfide after DRI treatment. We're effectively taking out over 99% of the sulfide being removed as sediment. This is a great result, and it gives us a 3-step process that follows nature's lead. Step 1 uses sulfate-reducing bacteria to convert sulfate to hydrogen sulfide. Step 2 takes DRI reactive iron and converts hydrogen sulfide to iron sulfide, insoluble iron sulfide. Step 3, that iron sulfide is precipitated out and removed from the system, eliminating sulfur completely from the water flow. This makes it impossible to recreate sulfate further downstream. So let's take a look at the results after all this. First off, we regularly are reducing, consistently reducing sulfate to sulfide. We have low capital costs. It's scalable. Nutrients only is our only input for the biological stage. Direct reduced iron takes out the sulfide. 100% renewable energy can be used for the power systems. Sulfate can be removed with Minnesota's own sulfate-reducing bacteria, our abundant iron, and Minnesota labor to build and maintain these systems here on the range. Thank you.